Hello, I'm HANXiao. The topic of our project is credit risk detection, classification detection of user fraud behavior. In this presentation, we will talk about the following contents: introduction, dataset, traditional models, FNN, result, and conclusion. In the first part, I will introduce necessary information about the research. Let's start with the abstract of the project. This research investigates machine learning techniques and models and uses these models to detect the credit risk behind loans by classifying the credit ratings. We take use of traditional machine learning models such as naive Bayesian, SVM, random forest, and XGBoost, and after making stacking integration on these models, we also build feed-forward neural networks and finally compare and evaluate the results. The following is a background. Risk management originated in the United States. It spread around the world with the rapid development of the Internet and the emergence of new technologies such as big data, data mining, and machine learning to make risk management more accurate. Credit risk, also known as default risk, is a possibility that a borrower is unwilling or unable for various reasons to fulfill the terms of a contract, thereby constituting a breach of a contract and causing a loss to the bank. Our project uses machine learning from Lending Club's loan data to build a loan default prediction model. Lending Club provides a variety of data about loans, including borrowers' personal credit information and specific loan status information. Based on the data, we classify and predict the risk rating about each loan, indicating the probability where the borrower will default on this loan and thus take appropriate actions to avoid possible losses. In this prediction model, we use 6 methods: naive Bayesian, SVM, random forest, XGBoost, stacking, and FNN. Here is a theoretical basis of each method. Due to the time limit, this section is simply passed over. In the second part, I will introduce the dataset applied in the research. The dataset we used in this project is a loan status table from Lending Club, which contains the loan status records from 2007 to 2018. Totally, there are 448,576 records in the dataset, and each record has 151 features, including 108 numerical features, which contains plenty of information to dig out. For example, there are not only some basic features about the loan itself, such as the loan amount and loan status, but also plenty of features containing information about the loan borrowers, such as the number of months since the borrower's last delinquency, and flags whether or not the borrower is on a HANXiao plan. The target feature we want to classify is grade, which is an assigned loan grade by Lending Club, containing 7 classes: A, B, C, D, E, and G, E, F, and G. Therefore, classifying the grade for a given loan is equivalent to detecting the risk behind this loan in the context of this dataset. The grade distribution in the dataset is shown in the histogram. After we obtain the dataset, we should pre-process the data. We proceed in the order of missing values processing, feature selection, feature encoding, and feature standardization. In the first step, we discard the records with missing values due to that a lot of machine learning models do not accept the missing values in training data and testing data. As a result, around 100,000 records are deleted from the dataset. Then, after looking through the detailed feature description document, we found several features are meaningless or are textual that our models cannot handle, such as ID, title, zip code. Thus, we discard these features directly. Next, we encode features in different ways according to the properties of their values. Finally, we carry out the feature standardization. Before training the model, we standardize the features by removing the mean and scaling to unit variance. The standard score of a sample X is calculated as follows. Standardizing the features is important when we compare measurements in different features that have different scale.
The fourth part is traditional model introduction. The first model is naive Bayesian. It's based on Bayesian's theorem and assumes that feature conditions are independent of each other. Here is a formula of the posterior probability. And the second one is support vector machine SVM. It can be used for classification, regression, and outlier detection. The objective of SVM is to maximize spacing according to the empirical risk minimization principle. The upper limit on the number of times a model can be misclassified is determined by the geometric spacing. Here is the hyperplane and decision functions. But when there is a noisy, we need relaxation variables, and when the dimension of the feature is very high, we need a kernel function to make the low-dimensional training samples into a high-dimensional feature space. The next model is random forest. It trains several car trees as a basic model to form a stronger model, and the new strong model have much better predictive power than the single big model. Random forest use random replay for both sample and features. It's from the algorithm of bagging. Bagging ensures that similarity between decision trees, which facilitates subsequent majority voting sessions. The best cutoff point from the current feature is found at the end of the inner loop, and the best cut feature is found at the end of the outer loop. Here is the algorithm flow of random forest. First, we play back sampling and build M cartridge trees. Build M number cartridges, and each cartridge selects the optimal feature and optimal cut point. And we do a voting, and the final result is the majority result of all the trees. XGBoost is based on the boosting tree principle, and boosting refers to two algorithms, the additive model and forward distribution. On the basis of GBDT, XGBoost submodels are built in parallel internally and are faster to calculate relative gradient boosting trees. The stacking method is to do model integration of our basic models. Here is a process of a stacking algorithm. The next part is the implementation of all the traditional models. Firstly, we set three evaluation indicators, that is accuracy, AUC, and macro F1 score. We can see the result of naive Bayesian. The accuracy is very low. And the confusion matrix means is if the data is concentrated on the diagonal part, we think the model classification result is good. And in the classification report, we can see the precision record, F1 score, support, and accuracy of our result. Here is the result of the support vector machine. We adjust two kernel functions. And here is the classification report and confusion matrix. The accuracy is better than the naive Bayesian. And there are parameters to be adjusted, that they are penalty coefficient C, kernel function, and gamma. Random forest, the prediction equation for the random forest prediction is shown in the formula. Here is the result of random forest. we can see the AUC score is extremely high. And the data is more concentrated than the previous two models. Here are a few parameters to be adjusted. There are number of trees, maximum depth of a single tree, and maximum number of features, and so on. The results of XGBoost show that each evaluation indicator is the best performance. Then we do model integration. But when we can see the naive Bayesian model doesn't perform well. So we set the first layer, select the random forest model and the XGB model, and the metal model select the SVC model for integration. Here is the result. We can see it is get a better result than XGB model. So that is end of that part. Thank you.
Okay. Our group is also build a feed-forward neural network for the classification. Let me simply introduce it at first. FNN model is composed by input layer, hidden layers, and output layer, and each layer has many neural units with parameters in it. The most important idea of FNN is a backpropagation algorithm which involves two phases. The first phase is forward phase. During this phase, the parameters of each neural unit are fixed, and the input is propagated through the network layer by layer. The forward phase finishes with the computation of the arrow. The second phase is backward phase. The arrow is propagated through the network in the backward direction, and the adjustments are applied to the parameters so as to minimize the error. In actual implementation, we construct the FNN model with two hidden layers, which each layer consists of 16 full units. And we use ReLU as the activation function for the hidden layers, which is a piecewise linear function that will output the input directly if it is positive. Otherwise, it will output 0. ReLU is the most commonly used activation function in the neural networks. For the output layer activation, we use softmax, which is also often used as the last activation function of neural networks to normalize the output to a probability distribution over predicted output classes. And we choose Adam as the optimizer for our model. Adam can be looked at as a combination of RMS probe and SGD with momentum. It uses squared gradients to scale the learning rate like RMS probe, and it takes advantages of momentum by using moving average of the gradient instead of the gradient itself. After the implementation, we train and test the model several times. Here is a line chart of the training loss in one training. We can clearly see that the loss decreased dramatically from the start of the training, and after the fifth epoch, the loss is decreased to 0.02, and the training accuracy is already exceed 99%. Then, after evaluating the model with testing set, we get a confusion matrix which could clearly show the detailed classification results. According to the graph, we can see that there are nearly no mistakes in classifying class A to F. Only few mistakes happen in the classification of class and G. The reason, I guess, is that the number of samples of F and G are less than other classes. But as a final result, the accuracy of testing set is almost 100%, which is very impressive in such a big data set. At last is the comparison and conclusion part. Here is the result table. We can clearly see that the naive Bayesian model has a worse performance in our dataset. It is probably due to the independent assumption between features. When there are too many features and correlationships between features that cannot be ignored, the bad performance is understandable. Next one is the support vector machine, which is usually perform well in a high dimension space. But this time, because the dataset is too large, it only achieves 81% accuracy at last. The random forest performs slightly better than SVM, but the major drawback of it is that it may have many similar decision trees that they cannot be found so it is not possible to get rid of the black box problem. XGBoost has the best performance among all traditional models, which is also an integrated model based on a decision tree, and it covers the most advantages of the random forest. The staking integration model is increased the evaluation indicator slightly than the XGBoost. We suppose that because SVC is placed in the second layer of the integration model as a meta model, its predictive ability is not very good, leading to not significant improvement after integration. At last, for the FNN model, it has the best performance that is way better than the traditional models. With an impressive accuracy that nearly 100%, the forward and the backward algorithm allows the model to memorize all the characteristics of different classes and store them in neural units as parameters. Finally, for the conclusion, after conducting many experiments, we clearly found that the FNN is the most powerful model for classifying the risk in loans, while XGBoost and Stacks also perform well in our dataset. But on the contrary, we also found that the naive Bayesian model is weak in handling the data with large number of features. That's all for our presentation today. Thank you all for listening.